to cover more the unit resolution type of instrumentation. So I will mostly talk about triple quadrupole and Q-trap mass spectrometers. But I also would like to spend a little bit time on more a couple of thoughts what is in front of the mass spectrometer, and combine it with a couple of data examples hot out of the oven. So a couple of thoughts around direct injection and sample preparation, and why should we use these things in combination with LC-MS for a different type of application, and then how we can quantify, identify our target analytes with very high confidence in water samples. If we think about sample preparation, again, as I mentioned in the previous webcast, we kind of like can follow two strategies, and both of them are very, very popular right now in water laboratories throughout the world. First, we can do the easiest and most cost-efficient way. We can filter our water sample and inject directly into the LC-MS system. That works very, very, very well with clean water samples. Drinking water is probably the most common example where this is used. This is definitely the best technique if you have to cover the widest range of compounds possible, especially if you have to include high polarity degradation products or metabolites of environmental contaminants, since these compounds are very difficult to extract from water samples. Here it's much easier to just inject them directly, and then depending on how low you need to quantify these compounds, you whether need a very powerful, a very sensitive mass spectrometer, or you have to inject larger volumes into the LC-MS system, which also is not a problem. And a modern high sensitivity MS instruments, state of the art, easily can detect compounds at a very, very low parts per trillion levels, depending on the compounds, maybe even sub-part per trillion levels. But also sometimes it makes sense to extract compounds from the water sample before analyzing with the LC-MS instrument. Online SPE is probably one of the preferred and most powerful, most popular techniques to be used. It can be useful if we have to achieve even lower limits of quantitation. Then we need to concentrate our target analytes. Estrogens would be a typical example where pre-concentration can be necessary to reach detection limits of interest. Sometimes if we have very dirty samples like wastewater, for instance, it's just necessary to clean up the sample, to remove matrix components, to make sure that we do not have too much ion suppression happening in the LC-MS instrument. And then, of course, sometimes there are tricky compounds. They have too high polarity that they cannot be easily analyzed with LC-MS. Glyphosate would be one example. Here we can combine extraction with derivatization procedures, and also that can be automated. LC-MS analysis, as before, if our goal is to detect as many compounds as possible in a single run, it's best strategy to follow very generic conditions. A plain C18 like the lunar C18 column or the kinetics C18 column are very good choices just to spread analytes evenly across the chromatogram to ensure they are separated away from matrix components. And we use very plain gradient conditions like water acetonitrile with a little bit of formic acid or ammonium formate. Very, very generic conditions. Keeping it simple here is very often the most successful way to deal with LC. If we think about the mass spectrometry, a part of the experiment on a triple quadrupole instrument, on a Q-trap instrument, running your sample in multiple reaction monitoring mode is the most popular, the most powerful mode of operation. Here we combine highest sensitivity with highest selectivity, and that's the ideal type of experiment for quantitative analysis. Because of the double filtering in Q1 and Q3, in MRM, we typically see very low noise, sometimes even no noise at all. And modern triple quadrupole instruments have fast operating collision cells, like the linear accelerator collision cell embedded into our instruments, which allows us to monitor many of these MRM transitions. And if we combine that with the scheduled MRM, we can maximize the number of MRM transitions even more. And that gives us access to multi-component analysis methods, and also for best data quality. The scheduled MRM algorithm is very useful, since it's optimizing the dwell time for each analyte automatically. Here's just a little schematic highlighting how scheduled MRM actually deals throughout the analytical run. When building our acquisition method in scheduled MRM mode, we provide retention time of each target analyte, and the software then is automatically generating these little windows around the retention time of every target analyte. And in areas where we have to monitor only a few compounds, the software will automatically use longer dwell times, and in areas to get the best signal to noise, and in areas where we have many compounds eluting at the same time, it will automatically use less dwell time to make sure that we collect enough data points for quantitative analysis. And this scheduling happens completely automatic. No user input is necessary there. And with our latest version of our data acquisition software, Analyst 162, we added a couple of more features into the scheduled MRM algorithm, like flexible windows for each compound. The window can be dynamically extended in case a compound is slipping in retention time, and then there are a couple of MRM triggered features which allows us to collect more MRM transitions per compound, or maybe full scan MS-MS acquisition to further increase our confidence if a particular compound is present or not. Here are some experimental conditions we used for the different type of data I will show you later. Some of the samples we injected directly, but we also recently did some work together with Gerstel, where we used the multi-purpose sampler with two autosampler arms to perform online solid phase extraction or disposable pipette extraction, a DPX, two very powerful cleanup procedures for our dirty water samples. We use different UHPLC systems for the analysis. The one we used was the Exigent Expert Ultra LC 110. The kinetics column, which is mentioned here, was used for PPCP analysis. For glyphosate, where I want to show you data, we used a Phenomenex Gemini column and a more tricky buffer with very high pH. And then for the different type of experiments, we use different mass spectrometers, all the way from the 4500 system to the 6500 system. The larger number the instrument has, the more sensitivity the mass spectrometer provided for analysis. We always used electrospray, operated the instrument in MRM mode with the scheduled MRM algorithm I explained, and in some examples we acquired MRM to MS-MS data. We used the MS-MS spectra to library search, which increased our confidence in identifying a particular pollutant in environmental samples. Okay, before jumping into the data, again, it's time for some polling questions.
Thanks, Andre. So two more polling questions for all of you. The first one is, what compounds or residues do you typically analyze for in water samples? Pesticides and metabolites, pharmaceuticals and personal care products, endocrine disruptor compounds, disinfection byproducts, microcystines or natural toxins, brominated flame retardants, perfluorinated compounds, polyaromatic hydrocarbons, or some other compounds? And what instrumentation do you currently use in your lab for your water testing analysis? GC, GCMS, GCMSMS, high resolution GCMS, LC, LCMS, LCMSMS, high resolution LCMS, or none of these? So again, what compounds or residues are you typically testing for in your water samples? And what instrumentation do you currently use in your lab for your water testing analyses? So the results are coming in. It looks like the majority of the audience are analyzing for pesticides and metabolites and some pharmaceuticals and personal care products. And it looks like the primary instrumentation being used is GCMS and HPLC. So Andre, any comments or thoughts?
Yeah, very interesting distribution. I'm not surprised to see that pesticides and pharmaceuticals and personal care products are the highest ranking topic. That is very, very typical. And then we have almost like one each for all the other different compounds being tested, which are very specialized laboratories and done here and there. And if we look into the instrument portfolio, also very, very typical, GCMS being a very important analyzer for volatiles, LC or LC-MS also present in majority of the laboratories. I'm just a little bit surprised that nobody is using GC-MS yet. That's kind of like the evolution of GCMS and probably becoming also more popular in the near future.
Great, thanks. And thanks to the audience for participating in the poll. So we'll go back to the presentation.
All right. So a couple of data using the method I described. So here is PPCP screening, a method we did some time ago. You see here the injection of a standard 0.1 microgram per liter of a mix of around 80 pharmaceuticals personal care products. We selected these compounds based on the method EPA 1694, and we used the scheduling feature to monitor these MRMs at respective retention times throughout the chromatogram. We used the Q-Trap 5500. We injected 100 microliter on column, and this allows us to monitor all these compounds at least 10 parts per trillion, directly injecting the water samples. For many of these targets analyzed, we had actually much lower limits of quantitations, but all of these 80 compounds could be monitored at least at 10 nanogram per liter. And of course, that makes it a very powerful method. We do not need to extract these compounds. We can inject the water sample directly, don't waste time and money doing sample cleanup. And we use that to monitor these pharmaceuticals, personal care products in all kind of like drinking and surface water. Here's just one example of Atrazine, one of the pesticides which was part in that panel. You see the chromatograms of 3 injections at 10 parts per trillion in the top. We are still quite a little bit far away from the limit of quantitation. We probably had an LOQ here of 1 or 2 nanogram per liter. Then we see the typical 3 to 4 orders of linear dynamic range for quantitation, and percent CV, a little bit tiny in the table, was well below the 5% for each of these concentration levels. And also I highlighted there the presence of the second MRM. Typically we recommend or also guidelines request that to monitor a second ion for each of the target analytes, and then the ion ratio can be used, can be calculated for each of the samples, and the ion ratio in unknown samples must be identical or inside of tolerances to our control sample, and this aids in identifying the compound, making sure that we detect the right target analyte at these low levels and not just some matrix interference. Here are a couple of samples. So that's a farmland sample collected nearby an agrochemical area, 100 microliter injected into the 5500 system, and you can see a couple of pesticides and also one antibiotic. These are all compounds which are widely distributed and found in the world. A couple of triazine pesticides, metolachlor at 6 parts per trillion, and sulfur dimethoxine are probably the most widely used and distributed antibiotic in the world. Here's a sample collected in a creek going to a small city in Ontario. And you can, on top of that, now see the influence of humans. So we can detect caffeine, cotinine, again, a couple of pesticides which are legally used here in Canada, people using in their backyards, and thiabendazole probably coming from people washing their fruits in the sink, and thiabendazole going through the wastewater system into the creek. On top of just collecting MRM information, we can also ask the Q-trip instruments on the fly to acquire full-scan MS information. That's done through some software piece called information-dependent acquisition. Every time an MRM signal goes above a threshold we can define, the instrument collects the MS information and then goes back to collect more data points for the MRM part for our quantitative analysis. And so here we get true quantitative and qualitative information in a single analysis. We can quantify the MRM chromatogram, and then on top of that we get the MS spectrum. We can search that against a library of different environmental pollutants, and then the library score, pretty much like in GCMS, allows us to identify compounds with very high confidence. That would be an example of it. The Farmland sample I was showing earlier was acquired using the scheduled MRM to MS mode, and we used our meta library for library searching, which contains more than 2,500 compounds. And you can see the MS spectra of the 4 compounds we found before. Full-scan MS spectra with good library searching results above 80 or 90% fit value. And I would like to remind you that we detected these compounds without any sample cleanup by direct injection at these very low parts per trillion levels. Okay, time for a couple of more of PBCP screening results out of our bigger water testing project we did some time ago with colleagues. One of the target analytes I picked for you is benzoylecgonine. Benzoylecgonine is the main metabolite of cocaine. Every time then BE can be found in water samples, that's some indication that cocaine was used in that particular area. And here are some results. The LOQ for benzoylecgonine was somewhere in the 1 or 2 parts per trillion range. In the red line in the middle, you can see that's the 100 parts per trillion level. We also injected as a control standard. And we had samples from different countries, different continents, from different type of waters, little creeks, drinking water, lakes, and rivers. And it's a good thing to know that the drinking water is almost free of the cocaine metabolite. We found it in a couple of creeks and lakes, which, for instance, includes the creek going through Zermatt in Switzerland, very beautiful and rich mountain village. And also we found it in the lake of Zurich in Switzerland. Here the human population distributes to the presence of the drug metabolite in the water. But we also found it in a very small lake in Canada with rich cottages around. We definitely can see some connection of the richness of the people living around the area and the finding of cocaine. And we find it in all different river samples all across the world. And this is quite a known fact. And actually, police is using such data to estimate the consumption of cocaine based on the concentration of drugs in different river samples going through major cities. And the other example I picked is atrazine. Widely used pesticides can be found in water samples in many countries in the world. Here we had lots of atrazine findings in samples we got from Canada and the US. It's a pesticide which is used here in the European Union. The atrazine is banned for many years already because of findings in drinking water samples, and we only had a single sample from Italy where atrazine was detected actually, and that's probably because it's leaching out of the sediment of that river. A couple of more examples now looking into the front end of the mass spectrometer, and that's work I did together with Oscar Cabrices from Gerstel in the US. We played around with disposable pipette extraction, which is an automated way of very easily cleaning up the sample. You can see our configuration in that little figure in the top, the Gerstel front end together with our 4500 system. The multi-purpose sampler does a couple of steps to automatically clean up our water sample or any other food sample we might want to analyze. It takes the sample, puts it into a test tube, and then it's using this pipette, which is filled with sorbent to aspirate the sample into this pipette tip, and then mix it a few times and discharge it back into the test tube. As a result, matrix components are bound to the sorbent. We clean up our samples, and following LC-MS analysis will experience less matrix effects due to that cleanup procedure. We also did some work on glyphosate, one of the high-demand analytes, but also they are very, very tricky to analyze. Glyphosate is a troublemaker for sample preparation, but also for chromatography due to its small molecular weight and high polarity. So here we used an automated FMOC derivatization, which is done by the Gerstel front end, followed by whether direct injection or online SPE cleanup, depending on our sample. And at the bottom, I put a screenshot of the Gerstel software where you can see the flow of analysis, which all happens automatically. The Gerstel front end is adding the buffer and the FMOC reagent. Then the sample is derivatized for a little bit of time, 20 minutes at higher temperatures, and then it's followed by an SPE cleanup, and then LC-MS analysis is performed, and at the same time the next sample goes into the derivatization until the LC-MS analysis is done. And as I said, that's completely automated and very powerful. Here's an example screenshot of glyphosate, glyphosinate, and AMPA, the metabolite of glyphosate, automatically derivatized and then analyzed using the QTRAP 4500 system. We injected 10 microliter, and here you see a concentration of 10 parts per billion, 10 microgram per liter. And if we go to lower concentration levels, so here's the analysis of 100 parts per trillion, 0.1 microgram per liter of injecting glyphosate, glyphosinate, and AMPA after automatic derivatization into the instrument. And due to the automation of the derivatization step, the analysis became very reproducible with a percent CV less than 5%. And here's another example where online SPE was used to identify and quantify estrogens at sub-parts per trillion levels. That is data which was done at the water laboratory in Langenau in Germany. I would like to thank Dr. Seitz for providing that data to me. You can see here different type of waters, pure water, groundwater, and untreated water, and the bottom one, that's a wastewater sample. They have been spiked with estrogens at 10 nanogram per liter level. We injected 5 milliliter into the online SPE system before then these compounds were detected on a QTRAP 5500 system, and the automated online SPE system here allowed us to quantify the 4 estrogens we wanted to detect at 0.1 to 0.2 nanogram per liter levels. With this, I'm at the end of this little presentation. A quick summary. LC-MS is a very powerful tool for the analysis of a big variety of environmental pollutants at trace levels, pharmaceuticals, personal care products, pesticides. As you told us also during the polling question, are maybe the two most important areas of water testing. Direct injection is a very powerful tool to skip sample preparation, to be very efficient, and also save time. With modern LC-MS instruments, limits of quantitation in the 10 nanogram per liter range or even lower is very easy to achieve. We can use ion ratios or Q-trap MS searched against library to identify these water pollutants with very high confidence. And then I was showing you a couple of examples how we can use automated front-end solutions like the Gerstel system we used in our laboratory to concentrate tricky analytes to reach even lower levels, or to clean up dirty matrices, to minimize possible matrix interferences and matrix effects, especially important when we deal with wastewater samples. And then also I was showing an example of the analysis of glyphosate, a very tricky polar pesticide, but has to be analyzed in water samples. Here we used automatic derivatization to get better extraction, recovery, and LC retention for better analysis. And with this, I would like to thank a couple of people who contributed to that presentation. Most importantly, Dr. Wolfram Seitz from the Langenau Water Laboratory in Germany, and Oscar Cabrices from Gerstel. And of course, also I would like to thank my colleagues for collecting water samples for me when they traveled last year on their vacation or while attending conferences. And with this, I would like to say thank you for listening. And if there are any questions, I would be happy to answer.